So now let's try to write some codes as a practice, right? So the first example that we're going to work on uh, is a one-dimensional problem. So here we're actually assuming xi is actually one-dimensional. So it's just a scalar. So uh, again, we are going to use this kind of porosity um, as the feature, and then we're going to classify uh, two types of rocks, sandstone and shale, based upon the porosity values. Right, and then we have a example data set. We're going to use a example data set, and this example data set is just a normal text file, and we're going to see how to load the text file into Python, and then we can use that testing data set to we can use that data set to do some experiments, right? So here I'm using my Python editor. It's called Spider, S-P-Y-D-E-R. If you haven't actually used it before, please refer to my previous videos and my videos on uh, hands-on start to Python, right? Hands-on start to Python. I have like 8 videos for talking about Python, and talk about how to install Anaconda. Anaconda is a Python package that includes Spider, this editor inside of it, and it's an interface that's kind of similar to MATLAB if you have used MATLAB before. So we have a big place for writing codes here, and then if you run the codes, you're going to see the results in this particular window, and then variables, file explorer, right, and then variable explorer, file explorer, and then help, right. File explorer, here you can see all the different files inside of this particular working directory, right, and then we're going to use a text file that's called porosity facies random.txt. It's a text file, right? We're going to try to load it first, and then we're going to train our model on it, and then we're going to apply the trained model onto this testing data set, right? So let's get started, right? Let's get started. So what are the libraries that we're going to import? We're going to import NumPy as NP, right? We'll have to use NumPy. NumPy is a linear algebra Python library, and then we are going to import some plotting libraries called matplotlib.pyplot as PLT, right? And then we're gonna try to load our training data. Suppose we write a comment here, load training data. So how are we gonna do that, right? We're gonna say training data is gonna equal to np.load text. It's a NumPy function. It's a NumPy function, and then because this text file we are loading is inside of the current directory, so I don't have to specify the entire absolute path for that file. So I can just write the file name, porosity facies random. For testing data, for training data, I'm going to use this particular file, right? Random.txt, right? And that's how I'm going to load the training data. Right, so let's just run this code and see what's going to happen. Oh, it's asking me to actually save the file, so I'm going to say that's going to be e6.py. Right. So I think it has finished running, right? So it has finished running. So and then I have a two-dimensional array in my workspace. That's called training data. That's exactly this variable name. And then the dimension of it is 198 rows and 2 columns, right? So if you are curious about what's actually inside of the training data, you can double click on it. And then it's going to give you this particular table, right? And this table is actually the training data set. So the first column is going to be porosity. So every row actually corresponds to a rock sample, right? You can think of it as a rock sample, right? This data set is actually from a well log. So if you are in the oil and gas business, or if you are a student in reservoir engineering or petroleum engineering or geology or whatever kind of profession that's related to well logs, you understand what this kind of data actually is. So the first column, it's actually coming from a segment of the well log, a segment of the whale log, and the whale log has been studied, has been classified manually by a professional, right? So the first column is going to be porosity corresponding to different the samples of the rock at different depths, and then the second column is actually the manual classification for that piece of rock, right? 1 means it's a sandstone, 0 means it's a shale, right? So we only have like 2 categories of rock, either sandstone or shale, right? So you can sort of see sandstone corresponds to usually larger porosity values, but shale corresponds to smaller uh, porosity values, right? That's sort of the format of this particular training data, right? So we're going to train our Gaussian model. In particular, we're going to try to estimate the mu hat and the sigma hat using this particular training data, and then we're going to apply this optimal model that's learned from the training data to a set of testing data that's not exposed to the training process, right? Okay, so we've got our training data, but now let's filter our training data into 2 categories, right? Let's select, right? So 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 we're going to separate our training data into 2 categories, and 0 is going to represent shale, and then 1 is going to represent sandstone, right? So we're going to say pore 0 is going to equal to the porosity for shale is going to equal to training data, right? Now we have to subset our training data. And the training data, the filter that we're going to use for selecting the training data is based upon the second column, which is the manual classification, right? So the second column of training data is going to have an index of 1 because Python is 0 indexed, right? So if the second column actually equals to 0, I'm going to take the first column of the training data, which is 0's column, right? So I'm going to select the rows with the second column equals to 0. And then I'm going to take those rows and then take out the 0's column. That's the porosity, right? So that's going to give me the porosity for all the shale inside of my training data, right? So now pore 1 is going to equal to, I'm going to get the porosity of all the sandstone in my training data, right? And then the 0's column, right? So that's going to give me 2 more arrays, pore 0 and pore 1. So now I can see that for the entire training data, I have 105 shale samples and 93 sandstone samples, right? And then if you add them together, that's exactly 198, right? But if we want to compute the prior based upon this kind of a proportion, we have to actually get the number of samples for sandstone and shale, right? So N0, that's the number of samples for shale. It's gonna equal to the size of pore 0, and then N1, that's the total number of samples of sandstone is going to equal to the size of pore 1, right? And then once we got the samples, we can compute the priors now, right? So prior, so how do we actually compute the prior? Do you still remember? Okay, what's going to be our prior, right? Our prior is just going to be the ratio. It's just going to be the ratio here, right? It's just going to be the ratio. So prior 0 is going to equal to N0 divided by N0 plus N1, right? And then the prior for sandstone is going to equal to N1 divided by N0 plus N1, right? That's going to be our prior. Yeah, I think that's the only place that I wrote down the prior, right? But that's how the prior is computed for the different categories. And then now let's try to get the ML maximum likelihood estimates, right? The maximum likelihood estimates are just the averages and the standard deviation. So for 0, let's call the average mean, right? Mean is going to equal to, NumPy has a specific mean function, right? For 0, that's the average porosity for shell, right? And then what's going to be the standard deviation for that? For 0, std is going to equal to np.std for 0, right? And then for 1 mean is just going to equal to np.mean for 1. And then for 1 std is just going to equal to np.std for 1, right? And that's actually our entire training process. And our training process is done. Training, right? So our entire training process only involves these 4 lines of code. Right. Of course, you can count those lines of code as a preparation for calling these four, making those 4 function calls, right? But that's pretty much all the training process that's involved, right? Once we got those best estimates based upon this specific criterion, we can make predictions now. We can make predictions. So don't forget these 4 quantities: for 0 mean, for 0 std, for 1 mean, for std. For 1 std were estimated just based upon the training data, right? We haven't actually used the testing data in any way, right? But now let's load the testing data. We are going to load the testing data in exactly the same way. Testing data is going to equal to np.load text, right? So this time it's going to be porosity. It's a different file now. Features test.txt, right? Right. Let's run this code and just to make sure that so testing data. So we have a testing data that's gonna look like that, right? The format is kind of identical to the training data, right? But it only got like 100 rock samples. It's still 2 columns, right? The first column is porosity, the second column is manual classification, right? We're gonna use the first column and then use our maximum likelihood estimates for the optimal posterior, right? To make a prediction about whether it's a sandstone or shell, and then we're gonna compare our prediction with this second column of the testing data. This is actually manual picks, manual classifications, right? We're gonna compare our prediction with the manual classification and see if the values are indeed identical, right, or different. So for testing, let's just grab the first column of it, because we're just going to use the first column to make our prediction. Testing data, the 0th column, right? That's our porosity, right? Then what's going to be the posterior, right? What's going to be the posterior? So how do we actually compute the posterior, right? We're going to compute the posterior using the exact expression. We're going to compute the posterior using this expression. Using this exponential expression, right? We're going to do that because here it's a 1-dimensional thing. So you don't. So d is going to be 1 here, right? So what's going to be our posterior? The posterior for testing data, right? For testing porosity. So y0, the posterior for shell for a given testing porosity, it's going to be equal to what? It's going to equal to we're going to type this part first, the exponential first, right? So it's going to be np.exponential. So because it's a scalar, so there's no need for this kind of transpose, this kind of operation. So we're just going to write it like this: for test. Let's reduce some typing. For test, subtract for 0 mean, right? And then this thing has to be squared, right? Because it's a scalar, right? If it's a vector, then we have to sort of do this linear algebra calculation, right? And then all we have to do is to divide it by 2 times for 0 std, the standard deviation squared, right? That's the variance. Standard deviation squared, that's the variance. Divided by 2, right? Divided by the inverse is just for the inverse of a scalar is just to do a division here, right? And that's it. And that's the exponential. That's all the exponential, right? So the line is going to be long. So I'm going to do a line continuation. Line continuation is this backslash, right? And then I can type the code on a second line. Here I'm going to sort of and then divide this term in the front. It's gonna be 2 times np dot pi times POR0 std, right? And that's gonna be the posterior for so prior 0, right? I have to multiply with prior 0, and that's gonna be my posterior for shell, right? Posterior probability for shell. And then we have to actually get another expression for the posterior probability of sandstone, right? I'm gonna copy it and then paste it. And then all I have to do is to change y0 to y1, right? And test 1. All I have to do is to change 0 to 1, and then put 1 std and then prior 1, right? And that's it. So that's the posterior for the two different classes, or the two different categories, right? And then what's going to be my prediction, right? What's going to be my prediction based upon these two posteriors, right? We're going to do this MAP. We're going to compare the probability and see which one is larger, and then we're going to pick the one pick the category for the based upon that, right? What's going to be my prediction? My prediction, let's construct an array. Construct an array that's called results, right? np.zeros zeros, np.size for test, right? That's gonna the result of my prediction is gonna be stored in an array filled with zeros, and the array is gonna have exactly the same size as the poor test, right? And then res, I'm gonna select y1 larger than y0, right? That's gonna be my filter for those elements with y1 larger than y0. I'm gonna set the result value to 1, right? And then I'm gonna compare my prediction with the actual manual pick in the testing, manual classification in testing data, which is what? Let's call it a phases test equals to testing data, the second column, right? And then I'm gonna print a summation of the absolute value of my prediction subtract phases test, right? So if I made any mistakes in my prediction, which is stored in this result vector array, right? Then the subtraction is not gonna be 0, right? Unless I made the correct prediction. Otherwise, it's not gonna give me the same phases ID or 0 or 1 according to this manual classification, right? And then I can do if I made a mistake in the prediction, then the subtraction is going to be either 1 or -1, right? And then I'm going to take the absolute value and then do a summation of that the absolute value vector, right? And see, let's run this code and see what's going to be the result, right? The result is 0.0. So it means that my prediction is perfect. I didn't actually make any mistakes, right? So that's going to be my prediction results, right? So what's so remarkable about this prediction result is not exactly this 0, right? It's not this 0. This 0 is kind of a very good result, right? But what's so remarkable about this result is that this posterior was computed entirely based upon the training data set, right? So this pole 0 mean and pole 1 mean and the standard deviations were all estimated from the training data. These formulas has never seen this testing data, right? But after we have applied this formula, the optimal model, onto this testing data, which was not exposed during the training process, we got a very good result. Very good result. That's so remarkable, right? That's so, now let's make some plots. Let's try to make some plots to visualize our results, right? So we're going to use some. So first thing that we're going to do is to generate the horizontal axis. X is our porosity, right? So mp dot a range. We're going to use the a range function to generate an array that goes from 0 to 1 with the interval of 0.001, right? And then P0 is going to be our posterior for our posterior for shield, right? So here I'm not going to type everything. I'm just going to copy some codes over to reduce my typing. So I'm going to copy some codes over. Right, so it's a very long line, so maybe I should just let me do a continuation, right? And then I'm gonna do a P1. So I'm gonna copy a bunch of codes over, right? And then P1 is the posterior for sand, right? For sandstone. Let me still do a line continuation here. And that's my two posteriors, right? That's my two posteriors based upon this horizontal axis. Both of them are Gaussian, right? And then I'm gonna plot these two posteriors as lines. One is as a black line, the other one is as a blue line. So shear are gonna be displayed as black line, and then sandstone are gonna be displayed as blue line, right? So, and then I'm gonna plot all the testing data, the lines are just too long. I need to break them up. Right, and I set the limit of the plot. And then if I run it, it's gonna make this kind of a plot for me, right? So the black is the probability for the shield, and then the blue is actually the probability for the posterior probability for the sandstone, estimated based upon all the training data, right? So the width and then the average value, the center, were estimated based upon the training data, and then the symbols on the horizontal axis is actually the training data, right? So you can sort of see this is not really a difficult classification problem, right? Because the separation between these two testing data sets are kind of quite wide, right? But what's going to be the intersection? What's going to be the intersection of these two different Gaussians, right? You can see the Gaussians has different heights, right? The reason that they have different heights is because of the prior 0 and the prior 1 has different values, right? Then what's going to be the intersection, right? What's going to be the intersection? So now let's try to actually determine this intersection, which is based upon this Fisher's linear discriminant analysis, or FDA, right? We have to solve this particular equation, right? We have to get a hat and b hat, and then we can solve for this critical porosity, right? So let's do FDA. Okay. So what's gonna be my common sigma? What's gonna be my common sigma, right? My common sigma, let's call it sig, is gonna equal to prior 0 times pole 0 STD squared, right? That's the variance, plus prior 1 times pole 1 STD squared, right? That's going to be my common sigma. And then the sigma inverse, later on we're going to use the sigma inverse, right? So sigma inverse, right? Sigma inverse is just going to equal to 1 divided by sigma, right? And then A is going to equal to what? A is going to equal to what? A is going to equal to sigma inverse times the subtraction of the two averages, right? So it's sigma inverse times per 0 mean subtract per 1 mean, right? And then what's going to be my B, right? What's going to be my B value? The B value is slightly longer. I'm not going to type it, so I'm just going to copy this code over. Right? And I'm going to break this line, right? So that's the prior. Okay, so this is still quite long, right? So let me, right? So that's my B, right? So you can sort of see that's per 0 mean times sigma inverse times per 0 mean, right? Subtract per 1 mean times sigma inverse times per 1 mean, right? And then add, divided by 2, the whole thing has to be divided by 2 with a minus sign, and then add the natural log of n0 divided by n1, right? And then what's going to be my x, right? What's going to be my x optimal? So I'm just going to print FDA x critical is going to equal to the discriminative x is going to equal to minus b divided by a, right? It's going to be minus b divided by a. So let's run it. Let's see what's going to be the x critical x value based upon this FDA analysis, right? Let's run it. And then the FDA x critical value is going to be 0.2069. So it's a 0.2069. That's about here, right? So it's actually a critical value that's kind of quite accurate. But don't forget we made the assumption that this sigma is actually common to all the different categories, or for the two different categories, sandstone and shale, right? But if we do not make this assumption, then we have to solve this particular second order polynomial, right? But for this particular example, because x is one dimensional, so we can still actually solve it, right? We can still actually solve it. And then what's going to be the exact value, right? If we actually solve this particular second order polynomial, right? The exact value is going to be very close, but we'll copy some codes over, right? So we're going to copy some codes over. Right, that's our decision boundary, but based upon some very long formulas, right? But it's an analytic solution. X1 is actually the analytic solution of the second order polynomial, right? And we have to call this function. Somewhere from our main routine, right? Main code. So decision boundary X, right? And it's gonna be quite a long function call, right? But it's okay. Right? This is actually obtained by solving this second order polynomial, right? If we run it, we're gonna be able to actually compare. The what exactly is x1? I can't remember what exactly x1. Right? X1 is anyway. X1 is not really useful, right? Let's run this code. So you can actually compare this FDA, the critical value based upon the FDA analysis is 0.2069, and then this decision boundary obtained by solving that second order polynomial without assuming a common, this common standard deviation or variance, is only slightly different. It's 0.202 something, right? It's not a huge difference, right? Which means that this assumption is actually reasonable for this particular example, right? And yeah, that's our and that is our first example for for doing this classification based upon a parametric model of Gaussian distribution.